Okay. And for today, we are going to cover our assignment last week. So last week, I wanted you to look at the astronomical images of all these deep sky object. And I have tried to find some. So let's go over them together. Uh, okay. Okay. My computer is frozen. The computer is dead. Oh, sorry. Probably I need to restart. Okay, that's much better. And we have a spotlight here. Okay, allow. Okay, let's go over the object and look at their images. The first object is a House-Taylor pulsar. So it does not have a good image, uh, probably because it is a pulsar and a neutron star. Um, Probably they're remnant. In the very beginning, they were there, but now they have all gone. So the physical property, what is important about the physical property of this object is the orbital decay. So if you look at the period, you can see that it rotates faster and faster. So that is the most important signature of this object. So it is in Aquila, and it is somewhere here in the upper right location. So they should be somewhere here. So I think one image that might be relevant would be if you have an image of the Aquila, look at the eagle here, and then you can identify this object that is about here, that is at the upper part of the left wing. So that is one possibility that they can give a question asking about this object. Okay, the second object is Sirius. Sirius, it is very bright. So the most significant feature of this image are the spikes. So all those spikes are in fact they are from the CCD. So this is basically means that when some pixels on the CCD, CCD is something like your retina in the camera, and when one pixel on the CCD, it is oversaturated, all the electrons in that CCD pixels will overflow, and it will overflow along two directions. So this is what is happening to a very bright object when you are observing with a telescope. So in fact, it is a star. So there is no way you can resolve it. So in fact, a dot in the sky. But when you are taking an image using a telescope, some pixels is oversaturated. So that is why you have a cross on it. That basically tells you that it is very bright. Yeah. So I have found some more details about this object. So it consists of series A and series B. The series A is a white main sequence star. So as before, it is an A-type star. So it is white because it is very young. So I want you to recall the sequence of the main sequence stars. So it is O being a good girl, kick me, right? So yeah, KM. And A is a very young and very massive star. So that is why it is very bright. So that makes sense. So it is a type A-type white main sequence star. So that is the very bright image over here. And the series B, it is a white dwarf star. So you can barely see it. I think it probably this, the very faint one. So you can see how different their brightness are. So you see that the stars will revolve around each other every 50 years. So yeah, this is something that might be related, that you can give a question out of it. Yeah. And it is a 20 astronomical unit apart. So one astronomical unit is the distance between between the Earth and the Sun. So they're not very far away. So it's just the 20 times the distance between the Sun and the Earth. Another interesting fact is that it is 8.6 light years away. So if you recall that the nearest star to our sun is about 4.3 light years. I think it's Centaurus, Centauri, Centauri Alpha, or Centauri something. Yeah. We can check very quickly. The nearest star. Oh yeah, Proxima Centauri. Proxima Centauri. And it's about 4.3 light years. So Sirius A is 2 times further from the sun. And it is the fifth closest star to the Earth. So yeah, so you know that between Sirius A, B, and Proxima Centauri, there are 3 stars between. Yeah. The name is derived from the Greek word cereros, which means scorching or glowing. Yeah, because it is very, very bright. Yeah. So it is located here in the about the bottom of the neck of this dog. Yeah, because it is basically here. It's very bright. So the brightest star in this constellation. Yeah. Okay, so that is for Sirius A and B. And the next object is Cassiopeia A. So this image is quite prominent. So I think you can see a lot of filament here, right? So this is a very typical signature of a supernova explosion. And as you see here, this is a type 2b supernova, and it has weak hydrogen lines. Type 2b supernova is created by some supermassive stars that they just collapse and explode. and all the energies are from the potential energies are released when the material collapse. And it has very typical, I mean also, the light curve will have a plateau, and that is one significant feature of the type 2 supernova. So let's take a look at the image. So this is the composition of the 4 images on the right. So different colors means different band. So if you look very closely, this is the combined together image for the other 3. And this is in silicon. So it is a trace of the pretty high ionized regions. So you can see there is a very high concentrations over here, here and here. So that means their emitting gas are located here. They're very close to the center. But by comparison, if you look at the argon line and the 21 micron dust emission. So those are tracing the dust around the in this nebula. Because so this tells you that this is the mid-infrared. So this is 21 micron. It is related to dust because dust, when they are pretty warm, I mean like hundreds of Kelvin degree. So they will emit in mid-infrared, and they will be very bright in these wavelengths. So you can see that the argon line and the 21 micron dust emissions, they correlate with each other. So they are tracing the dust. So these images tells you that different wavelengths will trace different part. So the silicon line will trace the inner part, and the dust will be outskirt of the remnant. And as the remnant evolve, I think the envelope will keep expanding, so that it will get bigger and bigger. So that would be the evolution. So the difference between type 1 supernova and the type 2 supernova is very important. So especially the physical origins. So I want you to remember that very clearly. Yeah. So Cassiopeia A is located here, even though it is in this constellation in Cassiopeia, but it's not within the main W. So it is somewhere here. Yeah, so that is their location. Okay, next is Myra, and this is a star. So if it is a star, it does not have the very prominent remnant features that you can resolve it. So because it's very big. So these nebulas or this remnant, they are envelopes exploded from the star, from the supernova. But for a star, usually you cannot resolve it. So it's basically a point. So it is so Myra is also a A-type star. So that is a Myra A, and a white dwarf, that is Myra B. So what makes Myra important is that it is variable. So you can look at the curve, the light curves that it shows here. So you can see that it is very variable, and it is periodic, and the magnitude can change so much, can change by 6, that it is very, very significant. So yeah, so the x-axis here, there are probably MJD, so modified Julian days. So basically 1 day. But starting from some point. So this makes it easier to calculate how many days, because it removes all the yearly features that in usual, coordinations. Yeah. So this is days. So you can see that so this starts from 4,8,700 all the way to 5,700. Yeah. So so you can calculate how many days the period is. So if you 507 minus 487, so that would be 20, so that would be 2000, right? 2000, that is 2000 days. So let's see how many period it is. It is 1, 2, 3, 4, 5, 6, 7. So 2000 days every 7 divided by 7. So that is about 300. Yeah. I think about 300 days for the period. Yeah, so in this way you can calculate the period of this star, of this variable star. So one fact about the Mira A is that it is currently in AGB phase. So that is a asymptotic giant branch AGB star. So it is in thermally pulsing AGB phase. So that is why it is variable. So each pulse lasts a decade or more, and the amount of time on the order of 10,000 years passes between each pulse. So with each pulse, Psychomira decreases in luminosity and the pulse grows stronger. This is also causing dynamic instability in Mira, resulting in dramatic changes in luminosity and the size of a shorter, irregular time period. So you see that, so the AGB phase is the reason for the variability of this star. But meanwhile, you need to know that the variability is not regular. So it is not periodic. So we can calculate some period, but that is not constant. So keep that in mind. So usually we might not use it as a standard cosmology candle. So we might not use that. Yeah. So Mira, we usually do not use it as a standard candle. Okay. But what we can use to use as a standard candle. So that is usually like type 1a supernova, that is one, and RR Lyra. So we will cover that later. So yeah, and for deep sky object Cygnus X1. So from the name, you know that it is very prominent in X-ray, because you call it X1, which means it is very prominent in X-ray. So in fact, this is the first actual galactic object detected when people launched the X-ray detector in the sky. So yeah, so it was the first one. So that is why it is very famous. Yeah. So the origin of the X-ray is a black hole. So what happening is that when the gas is accreted onto the black hole, it will form a disk. So as this image illustrated here, so it will form a accretion disk. Does anyone know why it is a disk? Why it is not a halo? Why it is a disk? Any idea?
Centrifugal force?
Centrifugal force. That is one, yeah, it's very related, yeah. But more precisely, it is because of the angular momentum. So because all the gas relative to the black hole, it has an angular momentum. So that means it must rotate around it. Otherwise, the angular momentum is not removed, so it does not fall into the center. Because if the gas need to fall into the center, it need to lose the angular momentum. And so when it is rotated, so you have the centrifugal force that will make sure that it's rotating the orbit. But in while it is rotating in that orbit, the angular momentum is preserved. So the gas need to find a way to lose all this angular momentum to force into the center, to force into the black hole. Yeah. Okay. So this is the image, and here is yeah. So this is the physical model of this object. So you can see here, it is in fact a black hole with a jet. So a jet is like shooting, like a hose. Yeah. So you're shooting gas out of it. So this is the physical model. So in the very center, you have the black hole and the accretion disk, and there are two jet in different ways. And all these particles in the jet, they are very high speed. So they are very close to the speed of light. So they're super high. So that's why it will generate some shock around it, and it will form some envelope. So this all this shock will give rise to the blue lights over here. So that is very big. So we observe that in a lot of black holes in the universe. Yeah. So this is the overall image. Yeah. So when you see a bowl like this, and so you know that, well, yeah, this is Cygnus X1. Yeah, Cygnus X1. So this is the feature that you are looking for. That is wavefront. Yeah. Okay. So one fact about Cygnus XA is that it is a binary system of blue supergiant and the black holes. So that is what illustrated here. So it is a blue supergiant around it, and it can shed the gas and feed that into the black hole. So that is how the black hole is ignited. Yeah. So supergiant variable. Here, it will provide gas. Okay, the next object is SS Cygni, and it is also in Cygnus. So this is the only constellation that has two deep sky objects. So this is so SS Cygni is a stellar remnant, and it is a binary system of red dwarf star and a white dwarf. So two dwarfs, but one is red and one is white. And it is a prototype of dwarf nova that shows normal eruptions. So you can look at the variability curves, light curves, and you can see that it is quite there are some periodicity happening, but not that irregular. So the reason for all these flares over here is the materials enforced onto the white dwarf. So here is the physical model that is happening. So on the right is the white dwarf, and on the left is the companion star. So one is a red dwarf, and one is white dwarf, and the gas are falling from the left to the right. So this is the flow of gas. Okay, shallow of the disk. Oh, interesting. Heated face of the star. So the white star is pretty bright. So because it is white, and the red dwarf is faint, and you can see that the red dwarf is illuminated by the white dwarf, and there are some shadow here. So this is the shadow of the disk. So there is a disk around it, around the white dwarf. So it will block the light, and it will form a shadow on the companion red dwarf. So that is very interesting. So you're seeing the shadow. And you can imagine that when the gas falls into the white dwarf, that it will give some instability in the disk, and the shadow side would change, and also the light would change. So that's why you see all these flares over here. And meanwhile, it also has a radio jet. So as long as you have some gas forced into an object, so you will form a accretion disk because of the angular momentum. Yeah. Yeah. So it is very special. Yeah, very special. Okay. The next object is supernova 1987. So this is a very famous object, and the image is very easy to recognize. So it's a ring. And so if you see a ring, you think, well, this is supernova 1987A. It is a type 2 supernova, right? And it is type 2 supernova the same as Cassiopeia A. So Cassiopeia A is type 2b supernova, and you have supernova 1987A, that is also type 2 supernova. So the light curve is very typical. So you see a plateau over here. It was the first modern supernova to be deeply studied, and paving the way to numerous insights into the nature and the behavior of core collapse supernova. Yeah. So the ring is the material that was shedded from the supernova. So because it is the explosion, and the shock wave and the material will keep going out. So in this case, probably it does not encounter much gas. So that is why it is very smooth and it is round. So it forms a ring here. But in the previous case over here, in the previous case here. Okay, yeah. Any question?
Oh, I need to leave now.
Okay, yeah, no problem. Yeah,
Bye. Thank you.
thank you. Have a happy Halloween. Okay, so this object it is quite filament probably because it encounters some interactions outside when the envelope expand. So that's why there are some shocks over here. So it's a sign of interaction. But by comparison, this one is pretty smooth. So probably not much interaction.
In
Yeah.
other words, not much stuff blocking its way.
Yeah, right. That's exactly what is happening. Yeah. So people will so you can trace the how it evolved along as time goes by. So this is the image in 1994, and this is the image in 2016. So you can see that, well, the outer part, I think it probably expand a little bit. But meanwhile, you can see the central part that there is a very significant signature of expanding envelope from the center all the way, and it gets diffused. Okay, so on the right, this is the whole image of this object. So the ring is just the central part, and there are some outer part over here. So and also you can see more signature of the interactions outside. So that is why it is called the cat eye nebula. So from this image, you see that, well, this is indeed a cat eye, right? So it's not just the central ring, yeah, but it had the outer part that makes it looks like a cat eye. Yeah. that is a supernova 1987A. Okay, let's yeah, there are still a few. Let's try to cover that in the next 10 minutes. So next one is NGC 6543. So that is a stellar remnant. So you look at the oh, this is cat eye. Sorry. The previous one is not a cat eye. So that is supernova 1987. Yeah, that is not a cat eye. Sorry. This is a cat eye. Okay. Cat eye nebula. Okay. This is a planetary nebula. The planetary nebula is not a supernova. So it is given right by a star for a sun-like star. So if the sun evolves into this stage, so it will be some nebula quite similar to the cat eye nebula. So you can look at the filament. The filament around it, so that is very big. But in the central part, you see that when you zoom in, so this is the cat eye. Yeah. Huh? Yeah. Yeah. Okay. So that is inside the Draco, that means the dragon. So that is a cat eye nebula. Okay, next object is R Lyra. So this is the variable star that you can use as to measure so you can measure the luminosity and measure the period, and they are highly correlated. So that is why you can use the period to derive the luminosity and then calculate the distance of this star. So that is the period luminosity relationship. So I think long ago, people did not know that there are two types of variable stars, but someone, I think probably Bard, he discovered, I think a professor in Caltech. So he discovered that, well, there are two types of variables. The one is R Lyra, and one typical one is Myra. And R Lyra can be used to trace, so you can calculate the period and use that to measure the distance. But for Myra, you cannot because it's irregular. Yeah. So the reason for the variability of R Lyra is the post-main sequence variable star. So it is just evolved out of the main sequence branch. So it just located here. So it is at this moment that it is the R Lyra variable. It is in this phase. Yeah. So it makes it very special. And meanwhile, Lyra contains Vega, also contains R Lyra. So Vega is not R Lyra. So Vega is the very bright star here. I think it's a little bit fainter than Sirius A, but it is still very bright. So that is Vega. But Lyra, where it is? Yeah, it's over here. Lyra is probably here, somewhere here. It's not that bright, but it's an 8th type variable. All being a fine girl, kick me. So all being fine. So it's still pretty bright. It's of 8th type.
Brighter than our sun.
Yeah, it's hotter. It's hotter than the sun. Yeah. Okay, next object is supernova 1604. So that is a supernova, right? So you see SN that stands for supernova. So 1604. So it's a type 1A supernova. So type 1A supernova can be used to measure the distance because its magnitude, its peak magnitude is the same for all type 1A supernova. So that is minus 19.2. So that is fixed. So that's why it can use to measure the cosmology distance. And it is first observed by Kepler. So that is Kepler supernova. It was observed in 1604.
There's also a telescope named after Kepler.
Telescope what?
Named after Kepler, right?
Yeah. Kepler is a telescope. So it's used to observe, to find actual planet. Yeah. So type 1A supernova. So type 1A supernova is that usually it's a binary system. The binary system, one is a white dwarf, which means that it's massive enough, but not enough to create a supernova. So it still misses some mass. So how to make up that gap? So it has a companion star. When this companion star reach some stage, for example, a red giant or super red giant, so it expand, and some of the gas will be accreted onto the white dwarf. So the white dwarf would grow bigger and bigger until at some point, it's big enough to trigger some nuclear supernova explosion. So that is why the mass is exact, and that is why its luminosity, how bright it is fixed.
Because it will always explode once it reaches 1.4 solar masses, unless it is two white dwarfs bumping into each other.
Right.
In that case, it could be bigger.
Right, that's very rare because it takes very long for two stars to merge. Yeah, that's very rare. But you see that because you see gravitational wave, right? So that is the merge of two neutron stars or two black holes. Yeah, we can talk about that
later.
Yeah, I think okay. The second to last object is Betelgeuse. Betelgeuse, yeah. So it is a star, and it's one of the brightest and most identifiable in the sky. It is variable, and it has some filament around it. So it is a red supergiant. I think probably that's why there are some signs of envelopes around it. But the light curve is highly, even though it is highly variable, but it's not periodic. Okay. Yeah. Betelgeuse is the 10th, second brightest star in Orion and the 10th brightest star in the night sky. Yeah, pretty bright. Okay, and the last object is gravitational wave 150914, because it was discovered in 2015, September 14th, and the location is in South Hemisphere.
Southern Hemisphere, which is very exact.
Yeah, but in fact, it's a area in the Southern Hemisphere. But for other two detections here, the one, the two here, that you can determine the stripe where it might be located, but it's possible in two directions. Yeah, but for the 150914, it is only possible in the Southern Hemisphere. So all these are done by modeling. Yeah. So this is the first direct observation of a gravitational wave signal. So it is a result of two black hole merge. So it will emit the gravitational wave. So I think in last invitational, they asked what is the mass of the two black holes, right?
Yes.
So I
It's
think
very hard.
6 points something. Let's try to look it up. So gravitational wave mass. So that is one is 36 plus 5 minus 4, and one is 29. So the mass. Yeah.
So very big.
Yeah, pretty big. Yeah, it's much bigger than white wolf. Okay, so that is all for today. Sorry. Well, thank you for coming.